I have a rectangle. So the length of this rectangle is 10 centimeter plus or minus 0.1 centimeter. The width is 5 plus or minus 0.1 centimeter. So the average area is 10 multiplied with 5, which is 50 centimeters square. The maximum area is 10.1 multiplied with 5.1. Calculate that. 10.1 times 51.51. 51.51. Similarly, the minimum area is 9.1 times 4.1, 4.9. Sorry, 9.9, not 9.1, 9.9 also, which is 10 minus 0.1. 9.9 times 4.9, 48.51. 48.51. The difference between the maximum and the average, maximum area minus the average area will be approximately equal to the difference between the average area and the minimum area. Okay, you can check that. They are approximately equal to each other. The difference here is 1.51, right? And the difference here is a little bit different actually. 50 minus 48.51, 1.49. 1.49. The percentage uncertainty or fractional uncertainty, I like to use the percentage rather than fractional percentage. There's actually similar percentage of uncertainty of the area delta A. This difference, I will call it delta A, which is the absolute uncertainty. Absolute. The ratio between this absolute uncertainty and the average uncertainty is the percentage of uncertainty. I can take 0.51 or 0.49, I'll take the middle value, which is 0.5. Let's take 0.5. Divide average value, which is 50 centimeters square here. This percentage uncertainty is 1.5 divided by 50, 3%, 0.03, 3%. From the example, the percentage uncertainty of the length, delta L over L, is 0.1 over 10, which is 1%, right? And the percentage uncertainty of the width, delta W over W, is 0.1 over 5, which is 2%, right?
Oh, that's 3%.
So you see that the percentage uncertainty of the area, 3%, will be the sum of 1% and 2%, which is the percentage uncertainty of the length and plus the percentage uncertainty of the width. See? 1% here and 2% here. Okay? See here. Let's try this example. So the first formula that you need to try memorizing and practice doing solving the problems, answering the question, is that when you have a quantity x equal to a over b, or x can be equal to a times b, it doesn't matter. It is the ratio or the multiplication, okay, division, multiplication. Percentage uncertainty of x will always equal to the sum of the percentage uncertainty of a and percentage uncertainty of b. For example, about the area, later when we practice with the question, you see that we apply this formula a lot, and it is extremely important for the paper 5 and paper 6. Okay, hopefully that we can do some example before running out of time. Raising to a power. The last thing, raising to the power here. I will take another simpler example rather than this one about the area again. Instead of a rectangle, now I would take a square, meaning the size, the length, and the width are the same. Here is A, the width is also A. Let's take example that 10 centimeter plus or minus 1.1. The width is also the same thing, plus or minus 0.1. Plus or minus 0.1 here means the absolute uncertainty due to the tool, the ruler that we use to measure the length. So the area of this square is A times A, right? A square. And similarly, we calculate the average value, which is 10 square, that is 100 centimeters square. Similarly, the maximum area is 10.1 multiplied with 10.1, 98.01 centimeters square. And similarly, the difference between the maximum area and minimum area and average area is 2.01. I can take it approximately equal to 2 centimeters square. And the percentage uncertainty will be delta A over A, 2 centimeters square over 100 half, 2%. And you see that the percentage uncertainty of this A, delta A over A, is 0.1 over 10, right? Meaning 1%. Okay? So this 2% is 1% plus 1%, and that actually 2 times of 1%. That is just simply we replace the width and the length by the same thing. And this one side and another side, the same value. Okay? So multiply with 2. So similarly, with another example, calculating the volume by this formula 4 over 3 pi r cubed. So each time we measure the radius, the uncertainty, fractional uncertainty, delta r over r, and you add them 3 times. So you have 3 times of the fractional uncertainty affecting the final uncertainty of the calculation of the volume. And therefore, the uncertainty of the radius, the uncertainty of the radius, delta r over r, is 0.02 over 2.5. Calculate that. 0.02 over 2.5 is 0.8%. 0.8%. So 2 times that will be 0.024 here, meaning 2.4%. 3 times of delta r over r will be 2.4%. So anytime when you see an equation that has the power, you need to take that power and multiply here, power 3, take the power 3, and multiply with the absolute, the fractional uncertainty. Let's do example, one example, then we stop. Test this out. An easy one, huh? Let's say about okay. Let's do do this one. What is the correct reading on the thermometer and the uncertainty in this reading? 24 degree. The 24 is absolutely correct, but what about the uncertainty? We have 5 bars here, 1, 2, 3, 4, 5, okay? So the smaller division is 0.2, right? 0.2 degrees Celsius, okay? We say 20, not 0.2, that's 2.
It's 1.
Sorry, that one was one division is 1 degree Celsius, 21, 22, 24, 23. So we need to take the smaller division is 1 degree, and therefore the uncertainty is half of 1.
Oh.
Yeah, which is 0.5. So the answer is 1.
Why does it have to be 24.0?
Because you take 1 decimal place for the uncertainty. 1 decimal place, okay? Question 3. Again, another one due to reading. The diagram shows the stem of a Celsius thermometer marked to show initial and final temperature values. What is the temperature change expressed to appropriate number of significant figures? Temperature change, initial temperature here and final temperature here. Initial is 11, 12, 13, 14, 13.5. No, minus. It's wrong. Sorry. This is minus 6, minus 7 here, minus 8, minus 9. Okay, so this is minus 6.5 degree. Okay, minus. This is 11, 12, 13, 14. So this final temperature is 14 degree. The question is the change. So 14 minus of minus 6.5. So the change is, sorry, need to put the other 0.5 down. Yeah. Is 20.5.
Yeah.